What we'll be discussing next is a special circuit element referred to as an operational amplifier. We're in chapter 5 of your textbook. Basically, we're going to induce the operational amplifier. These are called op-amps. And we're going to talk a little bit about some of the circuits that you can construct using an op-amp, as well as some instrumentation amplifiers. Now, some of these topics are a little bit advanced, and I'm going to, as we go through this, talk about the concepts of why these are important in electrical engineering. Many of you are either currently taking digital or you will take digital systems, digital signals, and so there are two worlds. There's the analog world and the digital world. And we've kind of put most of our focus recently in sort of modern electrical engineering on the digital world. But there are still a number of applications that are analog type applications. And so you find op-amp type circuits used in these analog applications. Some people, for example, are very picky about audio signals, and they really prefer the sound of audio that's been processed in an analog circuit as opposed to a digital circuit. So that might be one example. There are numerous examples, but we're just going to talk about op-amp circuits in the context of the analog signal processing world and show you some useful circuits that will be useful both in electronics and in circuits too, as well as in the lab. So they are typically called op-amps for short. It's the one example of a device that we'll cover in this class that contains a dependent source within the model. So it acts like a voltage-controlled voltage source. You can combine it with other elements, and it can look like other kinds of dependent sources. It basically performs mathematical operations on analog signals. So this class is basically created, and this textbook is written thinking that most of you are currently taking calculus. I know probably all of you have already had calculus 1 and 2 at least. Probably many of you have already had cal 3. But so in this particular class, we won't discuss things like integrators and differentiators, but I just wanted you to know that op-amp circuits can be made into integrator circuits. They can be made into differentiator circuits. And if there is time in the chapter on capacitance, I will talk about the op-amp integrator circuit and the op-amp differentiator circuit because it is interesting. So it's kind of like an analog, could be visualized as using op-amps to function in the form of an analog computer. So the op-amp is capable of a lot of different math operations. We already said that. We can do addition, we can do subtraction, multiplication, differentiation, integration. So on all op-amps, we have 5 inputs, and typically we have 8. But all have to have at least 5. There is the inverting input, the non-inverting input, the output, and the positive and negative power supplies. So this is, op-amps come commercially as chips. This is what the symbol looks like if you're doing like a chip layout. Balance is typically there to sort of make sure that things aren't kind of to have a calibration on your op-amp. You have a V plus and a V minus. And then this is what it would look like. Sometimes in this is your schematic. So if you actually draw a circuit, it looks like this. You have the inverting input, the non-inverting input. The inverting input labeled with a minus, the non-inverting input labeled with a plus. That does not mean that one of them has a negative voltage and the other has a positive voltage. So think of the plus and minus in the op-amp world as indicating non-inverting and inverting. Then there is an output. The V plus and V minus are typically left out of a circuit schematic. It is assumed that they are there. The offset null, a lot of times an op-amp, a real-world op-amp, will introduce a slight shift in DC, and so you can use these. There are little adjustments. You can use these to re-zero your zero voltage. So those are kind of things, practical things that make a difference in the lab. So here's just an example to show how power is hooked up to an op amp. Typically, people will refer to these voltages as the rail voltage. There's usually in a given op amp a specification on what the rail voltage can be. It typically varies anywhere from 1 to maybe as high as 10 volts, depending on the op amp. You rarely see op amps that will take voltages over 10 volts. So these are the two currents at the inputs. The supply is you almost always have a negative supply hooked up to what is referred to as minus VCC, and the positive end of the same voltage hooked up to the other terminal. And then the ground is usually centered. So you would have a minus VCC and a plus VCC for your power supply. I have some people in circuits too. Back when we were face to face, I used to have people build an op amp amplifier. Actually, it was a filter, and what they would do is sometimes they would not realize that the VCC, you had to have a negative and a positive. You couldn't have one of the ends connected to the ground. So that's kind of a common mistake in the lab. There are some op amps that do allow that because they have an internal system that will split the voltage. But the common op amps that you buy cheaply, you usually have to hook them up like this. It's taken for granted that they have to be connected, and typically these connections are not shown in the circuit schematic. Most op amps use two voltage sources, as we said, with a ground reference between them and a positive and negative supply voltage. Op amp is referred to, by the way, as an active element, and it does require an external power supply. So the op amp does nothing if it doesn't have this power supply connected to it. This is what they actually look like. This one has the little connectors that allow you to just plug it straight into a circuit board, and you can see the pins are labeled, and the pins correspond to different inputs. Pin terminal 8 is unused. Terminals 1 and 5, as I said, they're typically, or 1 and 7, 1 and 7 are typically used to like tweak things, actually. Okay, so pins 1 and 5, sorry. They're typically used to tweak things to get you like a balance on your DC voltage, as well as some other things in the lab to make the op amp perform like you want it to perform. Because as with all electronic components, they have a certain accuracy to which they're manufactured, and they're not all going to be 100% identical. So this is just a slightly bigger picture taken directly from your textbook that has a little less noise, where you can see the pin connection on the op amp, and then you can see a bigger picture of that op amp schematic. Now, in the real world, op amps are not ideal devices, and so they have an equivalent circuit. So here is our V1 and V2. That would be our inverting and non-inverting respectively. The VD is the voltage between them. It's V2 minus V1. There is this input resistance R sub I. Then there is, connected to reference, a dependent source called A times V sub D, where V sub D, remember, is this voltage here. So this A is a constant. V sub D is the input voltage, the difference between V2 minus V1, shown right here in this equation. And then there is the output resistance. And then the output is taken at the output terminal, and what's not shown here is that you take that voltage that's between the output and ground. So there's as we've discussed in the class before, voltage is always between 2 points. So this is always between the output and ground. And by the way, this V1 is also the voltage between this point and ground, and this V2 is the voltage between this point and ground. So a lot of times when we're depicting an op amp schematically, like in a class, we'll show like a common ground line that sort of defines for all of these where the reference is. So I want you to kind of keep this figure in mind. So VD is the voltage at the input terminals, RI is the input resistance, R0 is the output resistance, and A times V sub D is the dependent source that is outputting at the output terminal. So this is not an ideal op amp. A is referred to as the gain. It's a factor where you multiply the difference between the two terminal input voltages by a very large number. And so what that means is a very tiny voltage difference can give you an output. R is referred to as the output resistance. You would ideally like for that to be 0. You would ideally like for the input resistance to be infinity. So the reason for that is that you can actually use the op amp if you're running a system and you need, for whatever reason, to pass the voltage on to something, and maybe you need to do something to the voltage as you pass it through a system. The fact that this resistance goes to infinity means that these terminals don't draw any current. So at first that doesn't make any sense, because you would think, well, why would you want to use an op amp if you're not going to provide any current to it? But the op amp is there to do a particular job, and that's to pass an input to an output, usually with some kind of signal conditioning going on. And so because of that, you really don't want a bunch of current from your circuit running through the op amp. Remember, the op amp is powered by these external terminals that are not shown. So you want the op amp to sit there and do its job, but you don't want whatever circuit is over here supplying V1 and V2, you don't want that to notice that there's an op amp there. You would like for it to look like there's an open circuit. Why would you like that? Because if you don't have that, then this op amp itself pulls current from the circuit it's trying to measure or process. And so that's a problem, because then the circuit looks like it's got an extra load on it. So one of the main reasons op amps are used in analog signal conditioning is that they don't, what we call, load the circuit. They're not going to pull power from the circuit for the measurement device. So that's a very significant thing about op amps. All right, so here are some of the important parameters. A is called the open loop gain. It's open loop because in this circuit there's no connection from output back to input. Okay, if the output and the input are connected, that creates a different situation that we refer to as a closed loop or feedback, and that's not what we're talking about in this particular figure. So the open loop gain, you would like for that to be infinity. You would like to get an infinite gain out of your op amp. In reality, it is actually in the range of 10 to the 5th to 10 to the 8th. The input resistance, you would also like for that to be infinity. You'd like for that op amp input to look like it's an open circuit. In reality, that ranges from 10 to the 5th to 10 to the 13th ohms. The output resistance, you would like to be 0. So you would, now why is that? Well, let's go back to our equivalent op amp circuit. Let's erase some of this stuff so that we have kind of a clean figure to start with. Okay. Erase all my annotations here. So let's suppose for whatever reason you hook some kind of load up to your op amp. So we'll put a load out here. And the output voltage will just be then the voltage drop across this load. If this resistor is 0, then basically this voltage divider looks like this entire AV sub D gets dropped across the load. If this is not 0, then a couple things happen. First of all, if this is not 0, then you can have some heating, some resistive heating occur internal to your op amp device, and that's bad because these guys are delicate. But more significantly, because this would create a voltage divider, and the bigger this R sub 0 is, the bigger the voltage divider, or the more voltage drops internal to the op amp. So that means that you've got some power being dissipated in here, and you're also not getting the voltage that you've designed the circuit to give you. So typically the output resistance is 10 to 100 ohms, and then the supply voltage can vary from 5 to 24. Like I said, most of them, 10 is kind of a maximum, but there are some that go to 24. There are some that also are lower than 5, but mostly the most common range is 5 to 24. So you can see that this typical range of non-ideal values is pretty close to ideal values. So when we do circuit analysis of the op-amp, we analyze the ideal op-amp. And so that means a couple of things. It means we assume that the inverting and non-inverting inputs have the same voltage. So the voltage difference between the inverting and non-inverting inputs is 0. We assume the gain is infinite. That allows you to get an output for 0 input, and we assume no current flows into the input terminals of the op-amp. So those are the assumptions that we're going to make for an ideal op-amp, and you can find those literally in any textbook. Okay, what is feedback? So really, op-amps become most useful when we utilize something called feedback. Feedback basically takes the op-amp, the output of the op-amp, and it feeds it back into the inverting terminal. Now, you really do need to feed back to the inverting terminal, because if you feed back to the non-inverting terminal, you get something called a positive feedback situation, and that can cause the op-amp to become unstable. So you will note that in the circuits that we look at in this section of the book, there's going to be a feedback connection. Let me erase again. Kind of give you a feeling for what that looks like, because if you've never heard the word feedback or seen it used before, you don't have a feeling for this. So what feedback means is that you've got some kind of connection going from the output, and then a lot of times you have some kind of circuit in here. It can be a resistor, it can be various things. So it goes through something, and then it comes back to the input and connects right here. So this could be a resistor, it can be a resistor and a capacitor, it can be any number of things. So you've got that. Once you do that, you've created a feedback situation, and that's going to allow us to create some circuits that do some very useful things. One more thing to talk about as far as the operation of a real-world op-amp and the operation of an ideal op-amp. So ideally, the output voltage of the op-amp would not have any limits. But remember that the op-amp is externally powered, and that the source in the op-amp is a dependent voltage source. And remember, dependent voltage sources can't have an output unless they have some external power supplied to them. So what actually happens is, because of this and because of conservation of energy, the op-amp output voltage can't exceed the power supply voltage VCC in either the positive or the negative direction. So what that means is you have a range of voltage, of input voltages, over which you can operate, where the op-amp will be a linear device. If you exceed that range, so here's your V sub D. That's your V plus minus V minus. So that's the difference between your positive and negative, or your inverting and your non-inverting terminals. So if you exceed this on your input, you'll get saturation, and your output will not be linearly proportional to your input. That can be a huge problem. It can cause something called clipping. So suppose you take an AC signal and you put it into your op-amp. If you exceed the saturation on your output, you get this like funky thing that it like flattens out on the output side. It flattens it out because you've exceeded the saturation, when what you should get is, you should get like the full sinusoid. The saturation cuts it off. So people get all these weird signals in the lab, and they're like, oh my gosh, what's going on? My signal's all screwed up. Well, no, your signal's not screwed up. You've just, on your inputs, you've exceeded the limit, and you've saturated the op-amp, so it's cut your voltage off. So that, once again, is a common thing that you'll see in the lab. So the ideal op amp, let's talk about what that is specifically. You will have an infinite open loop gain. The resistance between the two inputs will also be infinite, and what that means is whatever it's attached to is not affected. So if you stick a node on the input or the output and hook a circuit up, what it sees is an open circuit. It's like the op amp is not there. It also has zero output impedance, and so this means that the Thevenin, from Thevenin's theory, this means that whatever you get on the output is load dependent. So let's see, lots of modern op amps come really close to these ideal values. A lot have gains greater than 10 to the 6th. Input impedances are often in the giga to tera ohm range, which would mean that current into both of your input terminals can indeed be estimated as being zero. So you indeed are not loading the circuit. When you operate this in negative feedback, the output adjusts so that the two inputs have the same voltage. So that's part of the power of what the op amp can do. So in the next lecture, we're going to look at some of the possible circuits that you can construct using op amps, and some of these do some very interesting things.